In this last section, we're going to be talking about waves, and specifically light waves. So we know light is an electromagnetic wave. That means it has an electric field portion and a magnetic field portion. It is a transverse wave in that the electric field and magnetic field oscillate perpendicularly to the direction the wave is traveling in. Now, some of the concepts we're going to be talking about here are specific to waves in general, and they were known before it was known that light itself was an electromagnetic wave. But again, we're going to focus on light in this last section. So this concept of diffraction, if we have a wave traveling and it comes to some sort of opening, say a hole, some sort of opening, like a hole or some sort of slit or doorway type situation, the wave itself the portion that can come through will start to spread over a larger area. Now, I'm a visual person, so just to kind of represent this to you, these are the simulations that we've been looking at. Here, just going to turn this on. This represents a water wave. As the wave is traveling, the colored lines, the non-black lines, are considered the peaks or the amplitude. But notice as it comes through the middle here, this middle portion here, see if this will let me write on it. So here, this would be considered a slit. It's some sort of opening. And notice the portion of the wave that actually comes through here is now spread over a larger area. So not only does it keep traveling, but if we were to represent what we would call light rays, or rays in general, meaning just lines, oh dear, sorry. I totally did not mean to do that. Okay, apologize about that. If we were used to use just lines to represent the direction the wave is traveling in, or packets of the wave, they are now traveling in different directions after they have come through this opening. In terms of water waves, I've been to one beach where I've seen breakers. They're big concrete barriers, kind of like these, so that when the big ocean waves, that's these blue lines are coming in from the ocean, a good number of the waves hit the breakers and then just crash off. And only a smaller portion of the wave, oh dear, I did it again. Smaller portion of the wave is actually allowed through those opening, the breaker. And by doing that, it makes the intensity of the wave decrease, because we now have only a portion of the wave and it's spread over a larger area. And then it just calms the waters. So of course we don't want that if you want to go surfing, but perhaps for an area on the beach to be family friendly for smaller children to not be totally tumbled over all the time. This same general idea works with light as well. So this generator, our light generator, if it was going to play, oh, no. Okay, well, we'll come back to that in a second. The general idea, though, is, That's why, sorry, I needed to play. The idea is even light that encounters some sort of boundary that has just a small opening, that light wave will also spread over a larger area. Okay, and general idea is the same. Let's see if we can get it to play this time. There we go. So the light that does come through that opening, that little slit, gets spread over a larger area. Now, if we change the size of the slit, the amount of diffraction, the amount of spreading changes as well. Watch this again. So right now I have the slit width fairly large, and that diffraction became less pronounced. In this middle region, in this region here, as these light rays continue, these look still fairly parallel to each other and nearly vertical. If I change the slit and make it smaller, the pattern spreads more in a semicircular way. It turns out the smaller the slit or opening, the more pronounced the diffraction will be. Now, this particular simulation also has another link called diffraction. This one represents the white dot in the big middle square, represents just a hole, a small circular hole, and the square on the right with the bullseye pattern represents the pattern we see because of the diffraction that has occurred. If I change the color of the wave, so the wavelength essentially, that pattern changes in size. It's still bullseye pattern, but the diameter of the circle changes. The other thing I can change is I can totally change the diameter of the hole. If I change the diameter of the hole and make it smaller, the pattern becomes bigger. So down on this bottom left, I'm changing the diameter of the hole. The bigger that hole is that the light can pass through, the smaller the pattern on the screen, meaning the smaller the diffraction. The smaller the hole is, the larger the diffraction. So we always see that with waves. The smaller the opening, the larger and more pronounced the diffraction becomes. Now, one other thing to show you in this particular setup, this eccentricity is a measure of how circular. So notice as I increase the eccentricity, it's making the circle become more and more and more oval, almost as if it's a horizontal line now. Notice the pattern here. This particular slide, this is the actual opening or hole. It's not working well. This is the pattern seen on the screen. Notice the hole or the opening is almost a horizontal line, but the pattern we see is vertical. The reason why, let's actually go back to our whiteboard to show that. Maybe. Oh, I gotta exit drawing. Now we can. So as we saw in that simulation, diffraction is biggest or most pronounced when the opening is small. The opening being the hole, a slit. When we had just a hole that was a circle, the pattern we saw was circles of light. So it's the same pattern, but we're seeing larger circles than the actual hole that the laser light was shining through. So the pattern we see is larger because of this diffraction. Now, it's not just due to diffraction, but the diffraction is the spreading of the wave as it passes through that hole. Diffraction is biggest or most pronounced when the opening is small. So when we took that circle and that hole and made it oval, it is smallest up and down, and it's largest side to side. That means the diffraction is going to be the greatest due to that up and down section. And that's why the pattern looked like these up and down lines. The diffraction was small. Diffraction was small in this direction. Diffraction was large, meaning the wave spread a lot farther apart because of that really small up and down portion. So diffraction is essentially the spreading of the wave over a larger area after it passes through some sort of opening. So the portion that can actually physically travel through the opening gets spread over a larger area. That's what we mean by diffraction. Okay? Now, in terms of seeing patterns on a screen with this light, that comes from the concept of wave interference that we talked about earlier in the semester. If you recall, if we had two waves that were identical, meaning they had the same amplitude and the same frequency, same wavelength, then if these waves had peaks exactly at the same time and location, troughs exactly at the same time and location, we said these were in phase, and we know that the result to the medium, the superposition, we just added the waves. We added the displacement, and we ended up with a wave that had twice the amplitude, but still the same wavelength. We said we got an instance of what is called perfect constructive interference. We could still end up with perfect constructive interference if one of these waves had traveled farther than the other. So let's see if I can do this. So these guys were in phase. If one wave is shifted, say, to here. If it's shifted, these peaks are still lining up. And please go along with me, these are supposed to have the same wavelength. The troughs are lining up. These are still in phase, meaning we would still add these together in the portion where we have them at the same location at the same time. We would still observe the perfect constructive interference. So earlier in the semester, we talked about waves coming from two sources, like two loudspeakers. If we had two sources, a x1 and an x2, x representing the difference in distance that the two waves had to travel. If this was a multiple of a wavelength, then we still observed this perfect constructive interference. And that was, of course, assuming the waves were in phase as they left the source. Well, as we talk about light, we can observe those patterns on this screen. So if we come back to this pattern, where we are seeing the bright yellow in this case is a location of perfect, sorry, the writing tool apparently is not very good in here, constructive. So perfect constructive interference is occurring here. All of the light up here in this laser beam shining on the hole that looks like this little oval produces a pattern. This is an interference pattern on a screen. The pattern we see, seeing alternating bright and dark spots, oops, let me exit that. It's going to change the eccentricity. The alternating bright and dark spots, the bright spots are locations of perfect constructive interference. The dark spots are locations of perfect destructive interference, meaning our waves met up where one had a peak and the other one had a trough. So when we added them together, they cancel. And so this is what we're going to be looking at. Diffraction is just explaining how the wave spreads over a larger area. And then interference of the waves is the pattern we see on the screen. We're going to look at the concept of one single wavelength of light, meaning a very specific color, shining on a slit and producing a pattern on a screen. Now this pattern here, notice it doesn't cover the entire screen. It covers just a certain area that still has the green light hitting it. If I change the wavelength of the light, say go down to red instead of green, without changing the size of the slit, the area, the width on the screen that shows red light ends up being a little bit different than the area that was showing the green light. Similarly, if we go over to blue or violet, the interference pattern we end up seeing on the screen ends up being a different width, is what we end up calling it. So the width here of this location where we can see the color on the screen, we would consider this constructive interference. That width is directly related to the wavelength of the light. It is also directly related to the opening of the slit, how wide the slit is. Okay. So if I increase the width of the slit, this simulation isn't perfect, but we do see this get brighter because more light can come through, but we also see the width of that bright spot get a little bit smaller. And that goes back to this concept of diffraction, where the larger the opening, the smaller the diffraction is. And so we see the width of that bright spot get smaller. We're also going to look at double slits, so light passing through two slits. Let's make the width of the slit smaller. There we go. When we make the diffraction more pronounced by making these slits closer together and wider, we can start seeing alternating bands of bright and dark. So again, bright, seeing the green means constructive interference. Dark, where we don't see any of the green light, means destructive interference. So that's what we're going to be looking at, is this combination of diffraction causing the light to spread over a larger area, and then interference of the different light waves that cause constructive and destructive interference. Constructive meaning we see the color on the screen. Destructive mean we don't see the color on the screen. So we're going to look at this in a few different situations. We're going to look at light passing through a single slit, a circular aperture is what that is called. So the circle, that one simulation I showed you that was a circle, like a little hole that's just a nice little circle, we call that a circular aperture. We're going to look at a double slit, so two slits side by side, and a diffraction grating. Our author goes in the order of double slit, diffraction grating, single slit to circular aperture. I like to go in the order I've written them, mostly because when we look at the pattern, which I'm going to show you some video clips and show you the patterns, we will see the single slit pattern when we look at the double slit experiment. So I want you to be able to distinguish what the single slit pattern looks like compared to the double slit pattern. So I just like to talk about it in that order personally.